Okay, so here's the lesson and examples for 5.3, angle relationships in quadrilaterals and polygons. So the sum of the interior angles of a quadrilateral, so all the angles added up inside of a quadrilateral, the sum is 360 degrees. The exterior angles of a quadrilateral also add up to 360 degrees. In fact, for any polygon, the angles on the outside add up to 360. So what does that mean? How do we explain that? Okay, we'll start off with the interior angles. What is the total of the four angles inside? Well, I just said and filled in the blank it's 360. But why? Well, one way to explain it is to divide the interior of that quadrilateral into two triangles. And two triangles, each triangle has 180 degrees inside of it. So that's 360. So there's an explanation. Now, I'm going to explain the exterior angles two different ways. I'm going to do it the hard algebra way first, and then I'll do the reasoning or logic way first. You see this line right here? I'm sort of filling in with the orange. Well, Z is equal to 180 minus the angle A, because it's a straight line, supplementary angles. I can do the same thing here and here and of course here, because I've got four sets of areas where we have supplementary angles. Now, if I take the left side of these four equations and add them up, I have W plus X plus Y plus Z, those four letters. And this total here, well, I have 4 times 180. That's 720, and I'm subtracting A and B and C and D. And what are those four interior angles? Well, we just said they're 360, so it's 360. So I've sort of shown that it is 360 because it's 720 minus those four angles inside. Is that the only way to explain it? No, that isn't actually the way I think of it, but that's one way to do it. So here's the other way to think about it. And this works for any size of polygon. And it's the interesting thing. Let's say I'm going to walk around this quadrilateral, the outside edge of this quadrilateral. And I'm walking along from B to A, right along here. I'm going to walk all the way around. Well, if I walk all the way around and I end up on B to A again, I'll have turned 360 degrees because that's a full way around. So I get to A here and I make a right-hand turn. Let's say, it's over 100 degrees. It looks like it's maybe even 125. I don't know how much it is. But we make a turn, and now I'm walking along here. I'll make another turn. This time it's less than 90 degrees, but I make a turn, and I turn Y degrees, right? So I did Z first, and then I did Y. And I get to here, and I make another turn, and I turn X degrees. Get to here, and I have to turn W degrees, right? And now I'm back. If I go all the way around, I'll have turned around, and I'm heading in the exact same direction I started off. I'll have turned 360 degrees. So those four angles have to add up to 360 degrees. Now, if it's a pentagon, a hexagon, any shape at all, to get all the way around, I'll have had turned 360 degrees. So the exterior angles like that are always going to add up to 360. So there's the reasoning way of doing it. Okay, so think about that, and then we're going to go on. Example 1. Find the unknown measure of each quadrilateral. Okay, so it's 360 minus the 56 minus the 95 minus the 98. I believe that's 111 degrees. The exterior angles are 360, so it'll be 360 minus 105 minus 50 minus 88. That's 117 degrees. Determine the angle properties of a parallelogram. Okay, well, we're going to do a couple of different things with this. Let's start off with the angles inside because they asked for angle properties. Let's say this angle right here, we'll call it A. How could we get angle A? Well, they said it was a parallelogram, which means opposite sides are parallel. Put the chevrons on like that, right? To get angle A, we could use PLT-C pattern. And then what about to get B? Right here. Well, it's PLT-C pattern again. And what about to get C? Right here. Well, PLT-C pattern one more time. So how would you describe the properties? This is 103. This is 77. This is 103. Well, opposite vertices, maybe that's what we could say. Opposite vertices have the same angle, right? And we can prove it using the C pattern. Okay, there's an angle property of a parallelogram. One other interesting thing, and this isn't the angles in the parallelogram, but if we draw the diagonals, and I'm going to erase this. You don't have to write this down, but I just want to show something. If I draw the diagonals, and I use the line tool here, and I draw these diagonals from opposite vertex to opposite vertex, then I have some interesting things happen. This length will be the same as this length. This length will be the same as this length. This angle will be the same as this angle. This angle will be the same as this angle. This angle is the same as this angle. This angle is the same as this angle. That's because of Z patterns. Cool. All right. Mid-segments of a quadrilateral. Okay, so, and I'm not going to measure. I can't really do it easily on the tablet anyways, but I'll demonstrate. So we'll find the midpoint of this side, let's say, and I'll show it's a midpoint by doing that and that. And then the midpoint of this one. And this one here, it's a lot longer. So again, I'm just sort of eyeballing it. I'm not measuring it. To be honest, I don't have a ruler at home. I didn't bring one home. I don't seem to have one around. All right. And depending on how accurately I drew that, it'll demonstrate this really well. But if you have a ruler and draw really accurately, you should or find the centers very accurately. You should have no problem demonstrating this. And what I want you to do is to draw any quadrilateral. Of course, the points, the vertices all have to face out. I didn't do too badly. And what this shows, and what is true for any quadrilateral, is that the mid-segments, and remember mid-segments join the midpoints of adjacent lines, will always form a parallelogram. Okay. The mid-segments of any quadrilateral always form a parallelogram. So draw yourself another quadrilateral, any one you want, as long as the vertices don't go in. So don't do a quadrilateral that looks like this or something. Although it'll work, it's just that parts of the parallelogram will be outside of the shape. Draw a quadrilateral, any one, and then draw the mid-segments, measure carefully, and you should have a parallelogram. All right, on to the next page. A ladder leans against the wall, making a 25-degree angle with the ground. What angle does the ladder make against the wall? Now, some of you are going to be really comfortable drawing these diagrams, and some of you are going to feel really uncertain. And that's normal. You get better with it as practice. So What do you start with? Always, if you can, start with the ground if there's ground. So let's draw the ground. Walls, unless something says otherwise, walls are always perpendicular to the horizontal or to the ground. Okay. Now, it says that the ladder making a 25-degree angle with the ground. This is actually ridiculous, isn't it? So this is the ladder. 25 degrees with the ground. What angle does it make with the wall? So now what they're asking for, and we'll put a little X there, is the angle it makes with the let's just get one thing out of the way. If you have a ladder set up like this, unless it's in a playground with everything anchored, what's going to happen if you lean a ladder like this against the house wall somewhere in your home or outside? The ladder is going to slide down and you're going to land on your face on top of the ladder. Not good. But this is 90, right? So to get the answer, we would take 180 because it's a triangle, minus 90 minus 25. And that is 75 degrees. Not 75, 65 degrees. Some of the angles of a triangle theorem. A hockey puck approaches the boards at an angle of 30 degrees. It deflects off the boards at the same angle it approaches them. What is the angle between the path of the puck before it hits the boards and the path of the puck after it hits the boards? So I'd like you to pause the video and try to make the diagram and then come back and watch the rest of the example. Okay, so you've got the diagram done. Maybe you have the whole thing worked out. So I'm going to draw the boards. And the puck is approaching at an angle of 30 degrees. And the way you orient this is somewhat up to you, but let's say 30 degrees. And then it leaves at the same angle. So now I'm going to label things a little bit. So boards. And this is the puck. Comes in at 30 degrees and then leaves at 30 degrees. The only thing the diagram is missing is, well, I didn't draw a puck, but that's okay, is what are we trying to figure out? It's always good to label. And I used an X in the last one. I'm going to introduce a Greek letter. It's called theta. Looks like an O with a loopy line going through it. Oh, I drew that pretty awkwardly. That's theta. It's a capital theta. It's a Greek letter. We often use it for angles. So if you see that, it's called theta. So what is the measure of angle theta? Theta, by the way, theta. Theta is 180 minus the 30 minus the 30, which is 120. Why can I do that? What's the authority for this? Well, it is supplementary angle theorem. The angle between the paths of the puck is 120 degrees. I didn't write a concluding statement on the one before, so I'm going to go back and do that now. What angle does the ladder make with the wall? The ladder makes a 65 degree angle with the wall. Last one. The equal angles of an isosceles triangle are each twice as large as the remaining angle. What are the size of the three angles? Okay, so let's draw an isosceles triangle, and I'm not sure what shape to make things, but the angles are on the bottom. I always think of it as at the bottom. Are twice as big as the angle on the top. So here's my isosceles triangle. I know it's isosceles because I say so. And these two angles on the bottom are twice as large. So let x be the smaller angle. And the larger angle will be larger angles. Will be what? Well, they're twice as large, 2x. So the two x's go here, the larger two angles, and this is x up here. Okay, so now we need an equation to solve. What do the angles in a triangle add up to? Well, 180. So 2x plus 2x plus x is equal to 180. 5x's are equal to 180. We divide both sides by 5. And x is 36. 2x's would be 2 times 36, or 72. The two equal angles are 72 degrees, and the other angle is 36 degrees. And that's it for the video.